Bismillahirrahmanirrahim. Let's start our new chapter for this course of heat and mass transfer. This chapter is chapter number 8 of Fundamentals of Heat and Mass Transfer by Incorpore and Dewitt, the title of which is Internal Flow. So as the name suggests, we would be solving problems for the flow through a pipe, for example. And these are some of the contents that we will be going over. I have listed the things over here, the topics over here, in the order of the sections of our book. So we would be starting with section 8.1, which says hydrodynamic considerations. Hydrodynamic means related to velocity, and 8.2 is then the thermal considerations related to temperature, heat transfer. So in here we would be discussing some flow conditions, the mean velocity and the velocity profile in the fully developed region, and then the pressure gradient and friction factor, the mean temperature in heat transfer, the Newton's law of cooling. Although we know what is Newton's law of cooling, but we would be discussing a related and important related aspect, and we would be developing a condition which we call fully developed condition. We will see what does that mean. And then we would be discussing the energy balances for the two cases that we had dealt with in chapter number 7, constant surface temperature case and constant heat flux case. So again we would be having the same thing, means while the fluid is flowing through the pipe, the temperature of the surface of the pipe may remain constant, or if it is to remain constant, then the heat flux would vary, and if the surface flux remains constant, then the temperature would vary. And then we would be looking at some of the laminar some of the correlations for laminar flow in circular tubes, and then some correlations for the turbulent flow in circular tubes, and we will also be looking at some correlations when the tube is non-circular, because it may be a square duct or a rectangular duct or duct having any other cross section besides circular. So we will see if the cross section is non-circular, how we can find out the convective coefficient and the heat transfer through those non-circular tubes. So these are some of the topics that we will be going over in this chapter. Now section 8.1.1 of our book is regarding flow conditions. What are we looking at over here is a sectional view of a pipe. So this is the length of the pipe. So this is the x, means this is the direction of the length of the pipe or tube, and this would be the diameter, and therefore this is the radial direction, in which this is the radius. Now in here it says that laminar flow in a circular tube, fluid enters the tube with a uniform velocity. So this is where the tube starts from, you may say, and the fluid enters the tube with a velocity of u. So what will happen then when the flow takes place over a flat plate? When the flow takes place over a flat plate, we have noticed the formation of a boundary layer. So over here there will also be formation of boundary layer, but what will happen is that the boundary layer will be formed all around its inner surface, 360 degrees. So there would be a boundary layer emerging from each and every point of the inner surface of the pipe, inner surface of the pipe, inner radius or inner dia of the pipe. So all those layers would get would then be having this uh, this trend, right? So if you consider this as a surface for a while, as a flat surface for a while, this is how the boundary layer starts forming, right? So boundary layer will not see, these are not two different, these are not two plates. Do not consider them as a plate over here on top and a plate over here at the bottom. No, these are not plates. As I have said in the beginning, it is a section view of a pipe, of a cylinder. So right now, if we consider the whole inner surface of the pipe, if we consider the whole inner surface of the pipe, you should be able to visualize it, that from each and every point on the inner surface of the pipe, what is happening? The flow is taking place, a fluid is flowing over a surface. Means convection would be taking place. And whenever the flow flows over a surface, whenever a fluid flows over a surface, the boundary layer forms. So the boundary layer would then be formed from each and every point of the inner surface of the pipe. So the boundary layers would start forming from each and every point, and if we take a look at those points which lie in the upper region, the boundary layer would then be formed in this particular direction, in this particular direction. So those boundary layers will keep on growing, as we have seen in the previous chapters, that when the fluid flows over a flat plate, the boundary layer grows as x increases. The thickness of the boundary layer grows as x increases. So over here the same phenomena is taking place. The boundary layer is growing as x increases, and all those boundary layers which are emerging from each and every point inside the from the inside surface, from the inner surface of the pipe, they will keep on growing. See, they will keep on growing. Their distance delta will keep on increasing. The thickness of the boundary layers will keep on increasing. The thickness of the boundary layers will keep on increasing until they will meet at a certain point. Of course, there would come a point where they will meet each other. So that point, or that length where the boundary layer, so after that the boundary layer growth will not take place anymore. So this particular region in which the boundary layer growth is taking place, boundary layer is being formed, its thickness is being increased. So this particular length is called hydrodynamic entry length, and this region is called hydrodynamic entrance region. What happens after this point? After this point, the velocity profile will become uniform. The velocity profile will become uniform, and that region is called fully developed region. That region where the velocity profile does not change, rather it assumes a particular shape, a fixed shape. So that region is called fully developed region. So there is an entrance region and then there is a fully developed region. In the entrance region, the boundary layer will keep on increasing until there would come a point that all the boundary layers will meet together, after which the velocity profile will become sort of constant, right? It will not change anymore. It will not change itself anymore, as we can see over here. Now this shape or this thing will continue on each and every x, on each and every downstream location. So that region is called fully developed region. So over here it says the boundary layers merge at the central line, and following this merger, the viscous effects extend over the cross section and the velocity profile no longer changes with x. So in the hydrodynamic entrance region, the boundary layer would have this shape, but it will keep on changing. But once the flow becomes fully developed, the the velocity boundary layer would then have that fixed shape. The velocity profile will no longer change. Of course, the velocities will be changing. See, in the fully developed region, what would be the velocity of the fluid over here at this interface? It would be 0 due to no slip condition. Over here it would also be 0. So the velocities will at each and every point all around 360 degrees on the inner surface of the pipe. The velocities of the layers which are in direct contact with the pipe inner surface would have the same velocity as that of the pipe. So if the pipe is at rest, the velocity of the layers of fluid at 360 degrees inside on the inner surface of the pipe would also be 0. And as we move away from the inner surface of the pipe, means as we move towards the center line, then the velocities will keep on increasing and the maximum velocity will occur at center point, because center point is the distance which is farthest from the inner surface of the pipe. The flow is then said to be fully developed. And the distance from the entrance at which this condition is achieved is termed as hydrodynamic entry length. This is what I have told you, that this length is called hydrodynamic entry length, and it is denoted by XFDH. X of course is representing length, FD means fully developed, comma H means hydrodynamic. So after this point, after this X, the flow would be considered as fully developed. Now over here we are starting with the same expression of Reynolds number that we have been using for quite long, which is velocity times length or diameter, since it is a pipe, so it would be diameter over viscosity. But over here we are no more mentioning U infinity. Rather we are using the notation of UM, and UM is the mean fluid velocity over the tube cross section. Mean fluid velocity. Why mean fluid velocity? As I was just explaining on the previous slide, that the velocity will change from 0 at the inner surface of the pipe to maximum at the center line. So there would be various values of velocities. Ranging from 0 to Vmax. So if we take the average of all those velocities, we would get a single average value of velocity, which we call the mean velocity, which we have represented over here. So instead of writing it as U infinity, because the flow will not, when the fluid would be flowing at any cross section, its velocity will in fact not be U infinity, rather it will change from a velocity of 0 to a maximum velocity at the center line. So therefore, while the flow is taking place through a pipe, we make use of this representation of velocity, that we write it as UM or VM, mean velocity. And what is the concept of mean velocity? It is the mean of different values of the velocities which occur inside a pipe, ranging from 0 to maximum velocity at the center line. Now, when we consider the flow through a pipe, the critical Reynolds number is said to be 2300. Means if the Reynolds number, if the flow is taking place through a pipe, inside a pipe, right? For the flow over a flat plate, the critical Reynolds number was 5 exponent 5, and over a cylinder or over a sphere, the critical Reynolds number was 2 exponent 5, as we have seen in previous chapters. But when the fluid is flowing through a pipe, from inside of a pipe, and if the Reynolds number is less than 2300, the flow is considered to be laminar, and if it is greater than 10,000, it is considered to be turbulent. And while it is in between 2300 and 10,000, the flow is said to be in transition. Now, for laminar flow, as it says over here, the hydrodynamic entry length. What was hydrodynamic entry length? It was that length after which the velocity profile attains a constant, a fixed shape, and after which we call it fully developed flow. So the hydrodynamic entry length may be obtained from an expression of this form. And so x FDH over D. X FDH means fully developed hydrodynamic length over D, diameter of that particular pipe in laminar flow, is approximately 0.05 Reynolds number. Therefore x would be 0.05 D times Reynolds number. So it is 0.05 over here, and Reynolds number as we have it over here, and we will bring this D on the other side over there. Right, so it would have D on the right hand side, and x FDH means L. We may write it in different notations. Over here L would represent the length, H means hydrodynamic in laminar flow, right? So it is the same thing whether we write it as x FDH or LH. Whereas for the entry length in turbulent flow, this was for laminar flow. For turbulent flow, this is the expression that holds. So x FDH means fully developed hydrodynamic length over dia must be greater than 10. So if x by d is greater than 10, as is mentioned over here, if x by d is greater than 10, the flow would be considered as fully developed turbulent flow. Right? So the first one is for laminar flow, this one is for laminar flow, and this one is for turbulent flow. This is a simple expression where Reynolds number is written in terms of mass flow rate. All you need to do is, because we know the expression of Reynolds number as mean velocity times diameter over density over viscosity. So we have got this now if you write this velocity as using continuity equation, mass flow rate is density times area times velocity. So if we write this velocity as mass flow rate over density times area, so we will come up with this expression. So it's a couple of step procedure, you can do it by yourself. And since we would have area, so it would be pi by 4 d square. That is why we are having a pi by 4 over here as well. Now this is the velocity profile in the fully developed region. As you can see that it is parabolic in nature, because its parabolic profile, the velocity profile is parabolic in the turbulent flow region. So this is the expression where on the left hand side it is u r over um, means u as a function of r. So u at r is equal to 0 would be maximum if r is equal to 0 is the center line, and if r is equal to the inner radius of the pipe, so then you would be having a value of 0 because of the no slip condition. So this is the velocity profile, expression of velocity profile, and we can see that it is parabolic. So these are some of the expressions that you would already have gone over in fluid mechanics course. Friction factor, Darcy friction factor. So I am going to skip a couple of slides, and then I am going to discuss the thermal considerations after velocity considerations. So previously we were looking at the velocity profile. Now we are looking at the temperature profile. So we have seen that the velocity profile develops, and it takes a certain length to get it developed, and that certain length is what we call the hydrodynamic entry length, and that region is called entrance region. So after entrance region comes the fully developed region, and then the velocity profile is fully developed, right? The same thing happens in heat transfer. Means that when the fluid comes in, now it will be now it will be the thickness of the thermal boundary layer. You can see that thermal boundary layer is growing over here, but it is not one single flat plate, rather it is a combination of infinite number of, you can say, flat plates, infinite number of points. So all those boundary layers would be emerging out, would be increasing in thickness as with an increase in x, and then they will meet at a particular point. Now this particular point is what we call entrance region, and if we are referring to temperature, we would call this as the thermal entrance region, after which the region is termed as fully developed region. Now over here, if we let's take a look at this profile. See, this is the profile. Kindly focus upon this profile. You would have seen this profile. You would have certainly seen this profile when we were discussing in chapter 1, right? In chapter 1, where we were discussing that how temperature varies. Now we can see over here that the value of Ts or Ts minus T infinity is decreasing. How? Because the length of this temperature or temperature difference is maximum over here, and then as we move away, consider this as a flat plate. Again, it is not a flat plate, but if for a second we consider it as a flat plate, so this is how the velocity profile will look like, because the temperature would be maximum, or the temperature difference between Ts and T infinity would be maximum at the liquid solid interface, liquid surface, not liquid, rather fluid surface interface, because it may be liquid or it may be gas. And then as we move away from the plate, the difference between Ts and T infinity would keep on reducing if Ts is greater than T infinity. If Ts is greater than T infinity, if the fluid is being heated up, now consider infinite number of plates over here, all around the periphery of the inner surface of the pipe. So there would be in fact infinite number of small plates. You can consider it like that for the sake of understanding. So there would be a velocity profile from each of those points emerging in this particular direction. So from the top it would be like that, right? And after a certain length, the flow would become more persistent. So its shape will become this shape. Now this is the expression that we have already gone over, that in the case of laminar flow, hydrodynamic entry length is 0.05 Reynolds number times d, and it was for hydrodynamic considerations. But when we come on to the thermal considerations, means when we talk about, kindly note the difference, that over there previously we had it written as x fd h, and h was referring to hydrodynamic entry length. Over here it says x fdt, and t is in fact referring to thermodynamic entry length. So x means length, fd means fully developed, t means thermal. Over d is approximately 0.05 Reynolds number times Prandtl number. So what is the difference between the hydrodynamic considerations and thermal considerations? In the case of velocity entrance region, so it was 0.05 Reynolds number. Over here it is 0.05 Reynolds number times Prandtl number. However, if the fluid is being cooled, then the temperature profile will be of this form. Because if the fluid is being cooled, it means that Ts is less than T infinity. It means that T infinity is greater. Now if T infinity is greater than Ts, then the velocity profile will be having this particular shape, where if we consider it for a second as a plate, again it is not a plate, but if for a second we consider it as a plate, so where will the temperature difference be maximum? It would be so it would be at far from the plate, and as we come closer to the plate, so that Ts or Ts minus T infinity would become smaller. Why T infinity would be larger away from the plate? Because the farther we are away from the plate, lesser would be the effects of the plate over there. But if we are close to the plate, so then if the plate is getting heated up, it means that if the fluid is being cooled down, so the heat will flow, the energy or heat energy will flow from the fluid into the plate. Now when the energy will flow from the fluid into the plate, then the fluid which is near the plate will not be at a higher temperature of T infinity. Rather, its temperature would be less than T infinity and closer to Ts. So that is why, for this reason, we see smaller temperatures or temperature differences in this particular region, and we see larger temperature or larger temperature differences at near the or at the center line. This is the reason. So this would be the temperature profile if it is getting if the fluid is getting cooled down. It means that if Ts is less than T infinity, so the fluid would be giving away heat energy to the surface, and this is how the velocity profile will look like if it is opposite, if Ts is greater than T infinity. This one is for the case where Ts is greater than T infinity. Now summarizing the things, the hydrodynamic entry length in laminar flow is 0.05 times Reynolds number times d, whereas the thermal the XFD means fully developed thermal or fully developed thermal length in case of laminar flow is 0.05 times Reynolds number times d times Prandtl number. So we can write it in this form. Right? We can then write it in this form. Similarly, hydrodynamic entry length for turbulent flow. Hydrodynamic entry length for the turbulent flow is approximately 10d, which is approximately the same as the hydrodynamic, which is approximately the same as the thermal entry length for turbulent flow. And in some cases we can use this expression as well. If you recall, we already have gone over this discussion where if the Prandtl number is greater than 1, then the hydrodynamic boundary layer would develop more rapidly as compared to the thermal boundary layer. Because we have discussed this thing while we were going over the topic of Prandtl number, which is in fact a ratio of delta over delta t. So if Prandtl number is greater than 1, it means that the numerator, which is delta, which is the thickness of the velocity boundary layer, is more than the thickness of the thermal boundary layer, and therefore of course hydrodynamic entry length would occur more rapidly as compared to the thermal fully developed length. Now there are three important points worth discussing, and they are regarding the mean temperature, and it's in section 8.2.2 of our book, and the title is Newton's law of cooling. However, these 3 points are very interesting. The first one is the one that we have already discussed. See, when it says that now in the case of internal flow, we will not be writing Q as HA times Ts minus T infinity, because when the fluid enters a pipe, it would not be at T infinity, rather it would be at different temperatures. and the value of the fluid which is near the inner surface would be having a temperature closer to Ts, and as we move away from the inner surface and closer to the center line, so then the temperature would be having a different value at the center line. So therefore, instead of writing Q as HA times Ts minus T infinity, it's better to use Tm. Now what is Tm? In fact, Tm is the mean temperature. Tm is the mean temperature, just like we had a mean velocity. Just like if I go back, I had shown you that there is a mean velocity, like that. So similarly, the temperature will also vary in this particular manner. So therefore, since it would vary from not from 0 to T max, rather it will vary from, let's say, approximately Ts to T infinity at the center line. So therefore, we may then represent, or we may take the means of all those temperatures or temperature differences, and then we may call it as Tm. So it says over here when a fluid is heated or cooled as it flows through a tube, the temperature of the fluid at any cross section will change from Ts at the surface of the wall to some maximum or minimum value at the center of the tube. Right? So if the value of Ts is greater than T infinity, it means that T infinity is less than Ts. So it would have a minimum value at the center line. The temperature of the fluid will have minimum value at the center line, and the fluid which is closer to the inner surface would be at higher temperature, and vice versa. Now in fluid flow, it is convenient to work with an average or mean temperature Tm that would remain uniform. Right? It is very important that it would remain uniform at a cross section. So it may vary from place to place, because it is because let's say if Ts is less than T infinity. So what will happen is that as the flow is taking place, the fluid will start getting heated up. So therefore, the mean temperature at one location will not be the same as the mean temperature at any other location. Or if Ts is greater than T infinity, if Ts is greater than T infinity, then the fluid will get heated up, and if Ts is less than T infinity, then the fluid will cool down. The point that I am trying to make is that Tm will change. It will not remain constant from location to location. Over here, as it says that unlike the mean velocity, the mean temperature will change for the reason I just mentioned. In the flow direction means in x, along the axis of the pipe. Whenever it would depend whether the fluid is being heated or cooled. If the fluid is being heated up, it means that T infinity is less than Ts. So if T infinity is less than Ts, the fluid is at a lower temperature, so it will get heated up. So Tm will increase. However, if the fluid is at a higher temperature, if T infinity is greater than Ts, so the energy will flow from the fluid into the surface, and as a result of which the fluid will get cooled along the flow direction. It means that Tm will decrease, it will decline. So Tm will not remain the same. The fluid properties in internal flow are usually estimated at the bulk mean temperature. This is an important point. In the previous chapters, we used to find out the properties of the fluid at the film temperature, which was the average of Ts and T infinity. Remember, we used to write Tf as Ts plus T infinity over 2. But over here, in the case of internal flow, the mean temperature or what we also call the bulk temperature. Bulk temperature would be the temperature of the fluid. It will not involve Ts. Rather, it will be the temperature of the fluid. Temperature of the fluid at inlet and temperature of the fluid at exit from the pipe. We will take the mean of those two temperatures and the properties will be evaluated at this particular mean temperature. Then the last point says that the temperature profile in the thermally fully developed region may vary with x in the flow direction. That is, unlike the velocity profile, the temperature profile can be different at different cross sections. As you can see over here, the temperature profile was having different was in fact different at different cross sections, unlike the velocity profile. Velocity profile, once fully developed, will have that particular constant shape, but over here it is not happening. And I suppose that you would have realized that why it does not happen. It does not happen because of the changing values of the mean temperature of the fluid. So because as I just discussed, Tm does not remain constant. If the fluid is getting heated up, Tm will increase, and if the fluid is getting cooled down, the mean temperature of the fluid will decrease from location to location. So therefore the velocity profile will have that shape, but that shape would be having different values at different values of x. However, this particular ratio would remain constant. This is what it says. However, this dimensionless temperature ratio would remain unchanged in the thermally developed region. Why it would remain unchanged? When the temperature or the heat flux at the tube surface remains constant. Why would it remain constant? See, this ratio would remain constant because T and Tm would then vary in proportion. The T and Tm would then vary in proportion. So therefore, what is Ts? Ts is the temperature of the surface of the pipe. Tm is the mean temperature of the fluid, which will vary at various locations. Right? So this temperature, of course, the temperatures would vary. There is no doubt that the temperatures would certainly vary as the fluid will flow through the pipe, inside the pipe, right? But this particular ratio would remain constant. Ts minus T over Ts minus Tm would remain constant for the reasons mentioned at the beginning of this slide and towards the middle of this slide.